And here we go. So the concentration of a standard solution, we can decrease the concentration by adding more water to it. Okay, if like for example, I always tell this story because my parents were they're old European parents, and my mom would always think that the orange juice was always too concentrated. Like if we just kind of spread it out a little bit more, it would last longer and it wouldn't be so orange juicy. So she'd always put water in the orange juice to kind of decrease the concentration for some reason, which was always a little bit weird, I thought, but looking back on it. But anyway, that's what she did. So she would add water to it to obviously dilute it a little bit so it would go farther. But that's what dilution is, okay? Dilution by definition is the addition of a pure solvent in order to decrease its concentration. So if pure water is used to dilute a solution, the overall volume increases, but it doesn't affect the amount of solid that's in there, okay? So I'm just going to show you here real quick here that in this little example here that we have, we're going to show this to you here, okay? So if I have a beaker, for example, okay, and this is kind of what they're doing here, and I just want to, I'll get you guys to copy this, obviously, but we have these these beakers here. These beakers are exactly the same, okay? They're the same size and everything, but we're going to start with a volume of 250 milliliters in this one, or 0.250 liters, okay? 250 milliliters, and the concentration is 0.10 moles per liter here, okay? And let's say it takes up to about, that's that much solution there, okay? And what they're saying is, if we just add water to this, so if we just go ahead and fill this up to 1,000 milliliters now, which by the way is a liter, okay? How does that change? What happens here? Well, obviously the concentration is going to go down, but here's what's going to happen. Let me just show you kind of here. We know that N is equal to C times V, okay? Or N in this case would be what? 0.10 molar times the 0.250 liters, liters, and that would be what? Right here I'd have 0.025 moles. Okay, so the amount of solid I have here is 0.025 moles in this beaker. Okay, that's how much NaCl I have. Now I could figure out the mass. That's not the point of this. Okay, I'm not worrying about that. But look, if we have 0.025 moles of sodium chloride, okay, I guess. Actually, no, I'm not going to worry about that. But if we had 0.025 moles of sodium chloride there, and then I just add water to it, so I increase the volume up to here, you know, the volume of a liter here in this case, how many moles do I have in this container now? 0.025 moles, right? I'm not adding any sodium chloride to it, I'm just increasing the volume. And by the way, I had to add 750 milliliters of water. Yes, make sure you write that in there as well. Okay. So I add 750 milliliters of water. I'm now at 1,000 milliliters, or a liter. I still have the exact same amount of solid. That didn't change. I didn't add any sodium chloride. I'm just adding water. So if I do N divided by V here, of course, N divided by V, we'll see that my concentration is now what? 0.025 moles per liter, okay, is my new concentration. So we can see the concentration's gone from 0.10 to 0.025, okay? So I've decreased the concentration, obviously. I've made this weaker by adding water, okay? Does that make sense? Okay, any questions, anyone? Now, luckily for us, they've come up with a formula. They said, hey, look, if this N right here, if this N has to be the same as this N here, if those two N's are the same, doesn't matter, okay, if you have it in 250 or 1,000, I add water to it, those N's are the same. Well, that's what that means right there, basically. Those two N's are the same. So the initial, okay, N has to equal the final N, okay? And again, you'll see we have a little formula here. What N is equal to C times V. So what they said is, hey, if the initial concentration and volume has to equal the final concentration and volume. So these are the initial conditions, and these are the final conditions. Okay, there. Sometimes when you go to university, you might actually see CI, VI equals CF and VF, or in textbooks sometimes you'll see that as well, where they talk about the initial and the final concentrations. And all we're doing is comparing these two, okay? That's all we're doing. We're just comparing them, okay? So basically they're saying, hey, if the amount of the first beaker here, if this amount here has to equal this amount here, then the first C1V1 here, C1V1, has to equal C2V2, okay? If the ends have to equal, then the concentrations and volumes have to equal each other out as well, okay, if that makes sense. Is that okay with everybody? Questions? So this is our dilution formula right here, and this is what we're going to use for dilution questions. C1V1 equals C2V2, okay? R2D2, C3PO, Chewbacca. There we go. Okay, so the initial has to equal the final, basically is what they're saying. I'm going to make one more comment on this here, and so I'm going to erase a little bit because I don't have enough room here. That's one thing I don't like about this whole system here. But look, what can you tell me about C1 versus C2? What do you know about C1 and C2 if it's initial and final? Tell me a general pattern that you would always see with all these questions. Has to be what? Anyone? Compare the two concentrations. What do you know about C1 versus C2? Macy? Yeah. Yeah, so this one has to be larger, and this one has to be smaller, yes? I mean, if you're trying to dilute something, you have to start out with something that's more concentrated, and it has to get weaker. The concentration has to go down. It goes down because we add more water to it, right? I mean, if you can do the opposite, I'd like you to let me know. We'd solve a lot of problems, yes? If we could, create something where we add water to it and the concentration actually goes up. Okay, that'd be amazing. So we know that. Concentration for one has to be larger than the concentration of two. What about the volumes? If we're adding water to it, the volume has to go up, and this would be smaller, right? So maybe we start, in this example, we start at 250, and it goes up to 1,000. Okay, so the volume always has to go larger. And that's how you set these two equal to each other. That's why they're equal to each other. Because obviously if the concentration wants to go down, then the volume has to go up. That's how we have to counteract that. Okay, good. Okay, let's take a look at our first example here, and then we're going to get into a little bit of different things here. So this one says here this: Elise adds 75 milliliters to 12.5 of this. Calculate the resulting concentration. So the resulting concentration in this case would be C2. This would be C1, and this would be my initial volume, of course. Initial concentration, initial volume. Now, we'll talk about this number here right away, okay? Now, I'm going to start with my formula here. C1, V1, C2, V2. This is what we're doing for homework today, basically, okay? We want to calculate the resulting concentration, C2, so I'm going to divide by V2. Boom, divide by V2, okay? Now, C2 is going to be C1, which is 0.905 moles per liter. Sorry, kind of ran out of room there. And we got 12.5 milliliters. Do I need to change this to liters? Question. That's milliliters there, by the way. Should I change that to liters? You have to. And again, if you remember, this is kind of one of those comparison formulas. The initial conditions to the final conditions. C1, V1, initial conditions, C2, V2, final conditions. As long as the units are the same, we do not need to change them, okay? So this is milliliters. And now it says that Elise, this girl here, is going to add to this 12.5. So what is my final? What is my final? Give me 1 second here. Okay, so yeah, so we have to add 75 in this case. So what we want as the final volume, if I start at 12 and a half, and I go and I'm going to add 75. So that should be a total of 87 and a half milliliters here. Okay. So let's see, 0.905 times 12 and a half divided by 87.5. And my final concentration is 0.1, let's see, 3 significant digits, 29 moles per liter. Okay. Good. Now, I'll mention one more thing about this here real quick, once we kind of get caught up here. Again, the milliliters will cancel with the milliliters, so we're going to be left with moles per liter. Now, if you're like, well, how do I know which ones, how do I know if I should use milliliters or liters in all these formulas that we're doing? Well, the answer is if you can't keep them straight, then I guess the default has to be liters, okay? So yes, you can always convert it to liters. However, okay, I'm going to tell you with dilutions, we usually talk about milliliters, especially when we get to the next part, which is something called preparing a standard solution from dilution, basically, which is we use stock solutions for that. It's probably going to be milliliters, okay? But again, liters does work. You just might have to, you know, if they want the answer in milliliters, you might have to convert it back eventually, okay? All right, now, most of these questions are not like this, okay? Most of the questions you're going to get, and I'm just gonna do it right here, okay? Most of the questions, it's going to talk about the initial volume, sorry, V1, is, let's say, you don't have to write this down, you can just pay attention, is 25 milliliters. They're going to talk about, okay, the initial volume is 25 milliliters, the final volume is 125 milliliters, okay? So you're not going to have to worry about that addition part. How much did I add? Well, I added 100, yes? That is irrelevant in the formula. That's what I'm trying to say, okay? So that doesn't matter in the formula. I want the initial volume and just the final volume. That's all I care about, V1 and V2, okay? That's all we need to worry about, all right? Is that good? Okay, so just keep that in mind. Most of the questions that you get, like in the homework today that we're going to do, they're going to tell you V1 and they're going to tell you V2, or they're going to tell you C1 and C2 and V1, and they'll ask you to find V2. But just keep in mind, if it talks about adding something in the question, then we may have to worry about this. We'll see. Most of the questions, like 98% of the time, they're going to tell you V1, they're going to tell you V2, okay? And we just go ahead and calculate C1 V1 equals C2 V2. Just, yeah, that's it, okay? Now, last part here today. We're actually going to skip this. Are we going to skip this? What do we got for time here? No, I think we could, let's do this maybe. This could happen. So it says here, this part, if two solutions are mixed together, okay, this is not dilution. Okay. So maybe I should have put this somewhere else, but this could happen. This is not a dilution question. I'm not simply adding water to these. I am mixing two different beakers together. And, you know, I did an example at the beginning of this unit where I mixed two solutions together and I got a precipitate. That's not this again, okay? That was two different solutions, two different compounds. This, if you notice, they're both NABRs, okay? They're the same compound. If I mix, you know, for example, Jada's got the first beaker here and I don't know, Tyler's got the second one, okay? Then we're just mixing these two together. What's the overall concentration? And the answer is, well, I'd have to calculate the total amount of solid and the total volume. Okay, so in the first beaker here, I just say this. Okay, in this one here, I have a concentration of 0.75 molar, and the volume I have is 250. Okay, I'm going to add this with another beaker here, which happens to be what? 0.288 molar and 350 milliliters of that. Okay. If I put them into one big beaker here, basically, to make sure that they all fit, because obviously I'm going to have this, I need to think about C equals N over V. Okay. In other words, what is the total volume compared to the total solute? Okay. So 250 and 350, I'm going to add those together down here. And 350. It's going to go down here. And I need to figure out N from this one and N from this one. And then I'm going to add those two N's for the total amount of solid that I have. Okay. So 0.175 and 250 is 0.04375 moles. Okay, C times V, that's what I did there, C times V. And I'm going to calculate C times V here as well, which is 0.288 and 350. And I get 0.1008 moles. I'm going to take those two and I'm going to add them together over here, 0.04375 and 0.1008 moles. Okay, I'm going to add those two together there. So I'm taking the total the total amount divided by the total volume, and that's my new concentration here. And again, this is not dilution, okay, because I'm not just adding water. I'm adding two different amounts of solids together and a total volume. Okay, but that's how I calculate the new concentration. If I do that, I get, and I'm going to divide that by 600 milliliters, basically. If you do this carefully with correct order of operation and all that, you should end up with 0.241 moles per liter would be your new concentration of that solution. Okay. It's not going to be just averaging those two, because you can't just average them, because we have different concentrations. We have different volumes of each one. And as you can see, you get different amounts from each one. Okay. So we have to kind of keep that in mind. Okay. So if you're adding two solutions together, same solution, but different concentrations and different volumes, you're going to have to figure out the total amount of solid and the total amount of volume. Okay. Is that good? Questions, anyone? All right. Now, this next part here is kind of the equivalent of what we talked about first in the first lesson, lesson 4. Okay. Now we're going to talk about a stock solution. And this is where things get a little confusing. But a stock solution is any standard solution that is diluted to prepare a new standard solution, okay, which is a little bit confusing. So let's go back to, just give me 1 second here. If we go back, you don't have to do this, but we went back to lesson 4 here for a quick second here. And remember this example right here, okay? So this is how I prepare a standard solution. I weighed out 1.2 grams, okay? I put it into a 100 milliliter volumetric flask. I filled it to the calibration line, and I mixed it up well, okay? So now I have this volumetric flask, or a foot, whatever, and it's full of water here, and this concentration is, what did we say we're making? 0.18 molar is 0.18 molar. Again, don't worry about this part. We'll do this tomorrow again as well. Even if you don't kind of understand this whole process, I'll go through the example with you tomorrow. It's not the end of the world. But we made this, this standard solution, and it's 0.18 molar. If I took this solution now, so I'm going to take this, and I'm going to make another standard solution from it. So I'm going to use another volumetric flask, okay, with the line here, and I'm going to make another concentration here, whatever that happens to be. So this now is what we call a stock solution. It was a standard solution, but I'm going to use that standard solution to make another standard solution. So this would be my standard solution here. Okay. If I made this one, it would be in stock, basically. I could put it on the shelf at Walmart and say, hey, guess what? We have some 0.18 molar lithium nitrate on the stocks on the shelf in Walmart. And then I'd say, hey, you know what? I don't want to make 0.18 molar. I want to make something weaker than that. Let's say maybe I want to make, I don't know, 0.10 molar. Okay. Well, I can use my stock solution, which was a standard solution, and make a new standard solution right here. Okay. And to make that even more confusing, if I took this one and I decided, hey, I want to make another one, this now becomes the stock solution, my 0.10 molar there, and I'd make another standard solution. And this one's maybe, let's say, I don't know, 0.05 molar. Okay. So that would be my new standard solution from a stock solution. Okay. And so on and so on. So that's what they're talking about here. Okay. And I'll show you that tomorrow. Now, when you're diluting a stock solution, you must calculate what volume of the stock solution is required. This is used, we use something called a pipette. A pipette. Okay. Now, a pipette, I did not grab one of these, so I guess I should maybe do that. Give me 1 second here. Let's see if I can find one here. Well, we'll go with this. Yeah, I'd see none of those are pipettes. No, still not. No. Okay, well, they look nothing like that. This is what happens when I'm not prepared. I will draw you a very, very bad diagram of what a pipette looks like. It is a skinny glass thing. It's not very long. It's probably, I would say it's maybe 2 of your hands together kind of thing. That's as big as it's going to be. It's not super large. That's about the size of it. And it's a very, very, very skinny, those are 2 parallel lines, by the way. And it's got a tip at the end here like this, okay? Basically kind of like that. And it's just got markings on it. They're usually in milliliters, okay? It's basically a straw. That's basically what I can tell you. And the tip is kind of very skinny, very narrowed down, okay? There is no valves on here. There is like no valves to stop any of the solution. And you know when, I'll use, I don't know if I can do this or not, but you know when you go to a McDonald's, okay, or Burger King or whatever, and you know when you take let's say you got your drink and your Pepsi or Coke or whatever, and you know when you put your thumb on the top kind of thing, and you pull out the straw, and it's full of like Coke or Pepsi. Do you know what I'm talking about? Yeah? And then if you take your thumb off of it, it all runs out, right? And if you're with your boyfriend, girls, he probably does that over and over again. And every time he does that, he's kind of like, oh, cool, right? Cool, right? And you just keep doing that over and over. That's kind of what that was supposed to be funnier than that. I guess it didn't really work, but whatever. I'm going to quit trying pretty soon. That's basically what this is. And that's kind of what we do. We basically stick this into a solution and put our thumb on top, and we make sure we get the right volume of that we need, and we basically put it into a new volumetric flask. Okay. And again, I'll show you this tomorrow, so don't worry about this too much here. But that's kind of what we're talking about here. And again, I promise I will show you this tomorrow. Now, this question here says this: the standard solution will be prepared in a volumetric flask if we need to make something where we accurately know the concentration of it. We have to use a volumetric flask. There's no other option, because the volumetric flask measures out a specific volume precisely, or as precisely as we can get it. Okay. Now it says here, describe how you would prepare a 0.10 molar solution by the dilution of 17.6 molar solution. Okay, and this is a pretty common type of problem here. In fact, this is exactly what I would do in the lab here if I was going to make these two solutions. We get it as 17.6 molar, which is pretty darn strong. Okay, it's probably got a pH of around 0, I would say, roughly, give or take a little bit. Okay, that's pretty strong. So we'd probably give you 0.10 molar. That's probably something more legit. So the first thing we notice here is this. Look, we have a concentration. We have a concentration. They're giving me two concentrations. I need to compare them. So I'm going to start with C1V1 and C2V2. Okay. Now, remember, we have two solutions here. This is different than the last one, lesson 4. Lesson 4, I was trying to make that original concentration, right? That original solution. I weighed out a solid. I put it into the volumetric flask. I filled it to the calibration line. I mixed it well. Now we have a solution. It's acetic acid, and we want to make a weaker solution. Okay, so I'm going to just go ahead and do this real quick here. 17.6 molar is going to go here. That has to be my original concentration, yes, obviously, because that's the bigger one here. I'm going to leave that blank for now. We want to make a 0.10 molar solution. I want to end up with 0.10 molar solution. Okay. Now, obviously, can I solve this at this point? No. Okay, how are you going to solve? This is 4 variables and I only have 2 of them. What's the missing number? Anyone? Yell it out. Don't be shy. Come on. Hurry up. Thank you. Now, 100 milliliters is our magical number. We always want to end up with 100 unless we tell you otherwise. In this case, it doesn't tell us. I want to make 100. Notice this word, describe. I'm going to need 4 steps for this as well. Okay, a couple things here. Now, here is the issue. Okay, I'm going to ask you, I want you to think about this. Where does the 100 have to go? V1 or V2? And I want you to think about that for a second. Where does the 100 need to go? Because about 3/4 of you are probably going to put it in the wrong spot. Sorry, that's just true. Where does the 100 go? Now remember, you're trying to make a new standard solution. The new standard solution, we have to accurately know the concentration of. Okay? How do we know the concentration? We make it in a volumetric flask. So I'll ask you again, where do you think the 100 has to go? V1 or V2 are your 2 options. V1 or V2. You have to make a standard solution. In other words, you have to end up with a standard solution. You put the 100 in what? V2. Okay? Always. All right? Look, we need to end up with something that has a volumetric flask at the end. Okay, we need to end up with 100. So we are going to solve for this case V1. How much of this do I need to take out? Okay, so if I go ahead and solve for that, by the way, it's going to be obviously V1 is what 0.10. I'm just going to skip a little bit here. 100. 17.6. Yes, you'll use units, of course, etc., etc. But it's basically going to be 100 divided by 17.6, and I'm going to need 5.7 milliliters. Okay. This was, of course, this was moles per liter here. This was milliliters, moles per liter, moles per liter, and moles per liter cancel, and we're left with milliliters. Yes. Okay. Is that good? Oh no, sorry. Did I screw that up? I maybe screwed that up. I did, didn't I? Sorry. That's, no, my bad. That's not true. 10 divided by 17.6 is what I should have had here, yeah? Sorry. I can't, I'm trying to do stuff without a calculator. Apparently that's not going to work today. Sorry, it's 0.57 milliliters. Is that correct now? Is that better? Yes, no? Yes, no? Okay. So, sorry, I should have said, sorry, it should be 0.57 milliliters. Okay. All right. And again, I'll kind of explain, I'll explain that to you right away here, but we should end up with 0.57. Okay. Now, we're going to use 4 steps here as well. Basically, how this works is this. Okay. I'm just going to go back up to here for a second. Don't do this, but just watch. If I took what color can I use here? 0.57 milliliters. If I took 0.57 of this, remember, that gives me N, yes? Obviously, it's not in liters, I get that, but that gives me N, right? So if I took that amount of solid, N, and I use that here with the V, I get the C here, okay? That's kind of what's happening in this question, okay? Without the whole extra stuff, that's what we're kind of figuring out. What amount do I have from the, how much do I need of that, what volume of that 17.6 do I need to get that N, to use that with 100 milliliters into the V, okay? And I'll explain this a little bit more tomorrow, but that's kind of what we're looking at there. Is there any questions on that, or do you want to ask any questions before we do the next part here? Anyone? Okay. All right, so step one. Now, remember, in the last lesson, we weighed it out. That's fine. That was a mass. We had to figure out how many grams. We don't have a solid here. We have a solution. So instead of weighing, I'm going to pipette out 0.57 milliliters of the 17.6 molar, you can say acetic acid or solution. Okay. So that's where I'm going to start. I'm going to pipette that out. Okay. That's how this one is different than the last one, because we're starting with the solution. 2, I don't need to dissolve it because it's already a solution. So there's no point in putting this into some water. I'm just going to basically place into 100 milliliter volumetric flask. Okay. The last one, if you remember the last example we did, was we dissolved it into 100 milliliter volumetric flask. This time we're just going to place it into a 100 milliliter volumetric flask. Okay. 3, we're going to do the same thing. We're going to fill it to the calibration line. 4, we're going to mix well. So 3 and 4 are fill to the calibration line with distilled water. We always want to use distilled water. If you forget that part, that's okay. But we always going to use distilled water because we don't want to introduce any other ions into this. In fact, if you pick the wrong ion to put into this, if there happen to be some copper 2+ or some calcium 2+, which naturally happens in water, it might actually make a solid. We don't want that. Okay, obviously, we would want these to be very clean and stuff like that as well. So mix well here. Okay, and we'd mix well. Okay. Is that good? And again, pipetting is a different thing. I just need to show you how that works. It's not quite super straightforward. There's always got to be a little thing that you need to worry about. So we'll talk about that tomorrow, hopefully when I'm there. But that's how we would prepare a standard solution from a stock solution. The biggest difference we have to understand here is this. In lesson 4, I'm just going to go back to that for a second here. We talked about making this standard solution. Yes. Describe how you prepare this 0.18 molar solution. Well, how do you make a solution? You usually start with a solid, okay? In this case, we put it into a certain volume of water, 100 milliliters, and we get this concentration, C. Okay? In this lesson, lesson 5, notice we started, I'm going to erase some of this stuff here. We started with 17.6 molar, and we want to make something that's weaker, 0.10 molar. We started with a solution, we're going to end up with a solution. That's dilution. Okay? I mean, you're only going to be able to add water. And of course, you're not going to go the opposite way, because how would you make something 0.10 to 17.6? How would you take something weaker and make it stronger? Not by adding water. Okay, that's not going to happen. Okay? All right. Any questions there? Anyone? Okay. So for the rest of the class here, we got about 20-ish minutes. We're going to hand out the dilution of solutions. Most of the questions are going to be based on, in fact, if I can maybe find that here, I will put that up here, but most of those questions are going to be based on dilution formula, okay, in some way, shape, or form. Unfortunately, I do not think I have the answers for this one. So you are probably just going to have to go ahead and do those, and we'll check them tomorrow. If I have time today at some point, I will see if I can find the answers. It's going to look a little something like this. Is this the one? Let me just check here. Yeah, here we go. So there's about 9 questions, okay? And again, it talks a little bit about dilution of solutions, okay? So just remember C1V1, C2V2 kind of thing, and that should be okay, I think, okay? So C1V1, C2V2 is basically what you're doing. Even if the concentration, if you look here, for example, even if this one here, let's say, just give me a sec here. Even if you look at, come on. This one here says, hey, I got 99.5%. I'm going to make it 3.75%. Even if I did that, that's still fine. That's still a concentration. It's still getting weaker. So I'm going from 99.5% to 3.75%. Remember, percent, grams per 100, they cancel anyway. So it doesn't matter what the units are. It's a comparison formula as long as the units are the same. Okay, that's the key here. The units have to be the same. Okay, so that's fine there too. Okay, if there's any questions, just feel free to ask. I'll let you guys work on that, and otherwise, let me know. Okay, I won't be going too far here, so just let me know. Just yell at me, whatever. Okay. So you guys have that worksheet there, I assume, yes? Okay, perfect. Okay, so I'll let you guys work, and let me know if there's any questions.